Hello, welcome to class Tuesday, April 21st. A few things. One, if you haven't finished the mock test, please finish that and get that turned in. Uh, the mock test, that grade that you'll get an actual raw score grade, and you'll get your grade from 1 to a 5. So if you haven't done that, try to get that in, or any other late work, please try to get those in. We're going to continue reviewing for the AP test today. We're going to do something a little bit different. Instead of AP test questions, we're doing some ranking tasks. I'm going to kind of keep doing this for a little bit, so to keep things switched up, just like all the other assignments, try to do them beforehand. Try to do them without looking too much up. When you find something that you don't know, kind of add it to your cheat sheet. Again, it's going to be a lot better to do your AP test if you just have like a short 1 or 2 page cheat sheet, as opposed to trying to just go through massive amounts of notes. Or if you're going to have a large portion of notes, you could split them up by topic, like maybe 1 page per topic, 1 page for 1D kinematics, 1 page for projectile motion, 1 page for forces. But it should be something that's really well organized. Otherwise, it's not going to be any help, and you're going to waste all your time trying to read through things. All right, so if you're watching this and you haven't attempted these, please attempt them first. This will be similar type of rules to the AP scoring. Obviously, there's no rubric to grade yourself on, so you're not going to give yourself points for grading. But I do want you to go through and actually attempt these. It would be nice if you print these out. Obviously, not everyone has a printer, or you might be having to share a printer with a parent who actually needs a printer for work. So if you have access to a printer, you can print it out. Otherwise, it would be nice for these just kind of summarize what the thing is asking. So you're just right here, just say rank the accelerations for the following, give a simple sketch of the pictures, and then a simple explanation: object dropped, rolling down incline, rolling up incline, motionless, and then just draw those. So I do want to see these actually simply sketched out, and a simple explanation of what you're doing here, so you can look back on them. You'll go through, you'll rank yourself, we'll go through, and then I'll give you the answer, and then you say whether you got it right or wrong. But as with everything, I care a lot less about your ranking. I care a lot more about your explanation. So the thing I really want you to focus on here is trying to do your explanation. When you write out your explanation, some of these are going to be really math. So like a lot of math, you can go through and do that. But I want you to put some words explaining your math. Don't just write out the math here and let that be the end. If you do math, go through and explain. Again, I care way more about your explanation. This is where you should be focusing most of your time on this, because this is where you're going to get most of your points on the AP test. All right, so let's go through this. We're trying to rank accelerations here. So it starts off pretty easy. So let's go with the easy ones. What are the easy accelerations to get? Just write the letters up in the chat, and then maybe put the acceleration for that. So B and C, it doesn't specify, but we're going to say B and C roll without slipping. All right, so some easy ones. So we're on accelerations 5. So A is pretty easy. A is just falling straight down, so the acceleration is due to gravity is negative 9.8 meters per second squared. And then for your explanation, you can just say falls with acceleration due to gravity. And notice how I'm going through and trying to answer these before I actually try to rank them. This is a good thing to do, try to answer the question before ranking. What are some other really easy ones? I would say there's 3 more really easy ones. D, yeah, D is real easy. So D is on a table, so it's just sitting there at rest, so my net force is 0 newtons because it stays at rest. And again, the key word here is stays at rest. It just sits there staying at rest, and that means my acceleration is 0 meters per second squared for D. The ramps, the ramps are a little bit trickier. I'm going to get to the ramps in a second. Those are the two that are going to have the most nuance out of all of these. E and F, what types of acceleration do E and F have? So E and F have centripetal acceleration. So I look at E. So this is going to be centripetal acceleration is speed squared over radius. Well, they give us speed. So 4 squared over 1 equals 16 meters per second squared. All right. Now, we could go through and try to do this with a free body diagram, right? We're at the bottom. So we have a tension holding this thing up. It's swinging on a rope. I have a smaller gravity down because this thing is swinging down. It's going to start going up. So I could try to do centripetal force is tension minus the weight of the object. But I don't have enough information to go through all of this, right? I don't know the actual mass of the object. I don't know the tension. So I can't do this. So this ends up not being useful. But keep that in the back of your mind for other things that we might end up using with this question. And then F is another thing going in a circle. Constant speed. So here we're in the equilibrium position of the pendulum, so there's no restoring force. There's no side-to-side force here. But it is still turning, right? Because the motion for E is going down and then up. So it has to turn. We have to have a upward net force. So we have to have a bigger tension force up than weight down because we're going to start moving upward. So the tension is not equal to the weight for a pendulum at the lowest point. Yeah, that's a tricky one. Pendulums are a little bit trickier. If it was a spring at equilibrium, then the spring force and the weight would be equal. But yeah, the pendulum is a tricky one because we have to talk about the tangential acceleration and the centripetal acceleration, right? So you're right. At the equilibrium at the lowest point, there is no side-to-side acceleration, so it's not speeding up or slowing down, but it is turning, and that is an acceleration. So that's the same thing with F, constant speed, but this thing is turning. So constant speed, but turning. And so because it's turning, therefore it has a centripetal acceleration. And so we are going to use centripetal acceleration as speed squared over the radius. It's moving at 5 meters per second. Square that, divided by a radius of 2. 5 squared is 25. Divided by 2, we get 12.5 meters per second squared. All right, so these are pretty straightforward, just simple math. And then it's asking magnitude of acceleration again. So this one, we really do need to use magnitude of acceleration. So the magnitude of acceleration in A is 9.8 meters per second squared. All right, now B and C. B and C, these are the ones I'm going to argue are the more difficult ones. There's a lot more nuance here. So let's start with B and C together. Where do you think these are going to rank compared to these? Which two should we really be comparing B and C to between A, D, E, and F? Which two of those letters are B and C going to be between? Yeah, A and D, right? We're on a ramp. So we're on a ramp. Our acceleration isn't going to be 0 if we're on the ramp. We are accelerating. It's either going to speed up or slow down while it goes up or down the ramp. And the thing pulling it is going to be acceleration due to gravity. So acceleration due to gravity can pull up to 9.8 meters per second squared. But if I'm on a ramp, we're going to be below 9.8 meters per second squared, right? Because the acceleration on a frictionless ramp, acceleration frictionless ramp, would be equal to acceleration due to gravity times sine of the angle, which is going to be less than acceleration due to gravity, as long as it's not a vertical ramp of angle of 90 degrees or something trivial like that. So it has to be less than acceleration due to gravity. So I know B and C are going to be somewhere between A and D. So B and C are going to be between A and D. So we just kind of have to figure out which one of these is a bigger acceleration, which one is smaller. So first of all, is this a frictionless ramp? There's a key word here that tells us if there's friction or no friction. Let's say I have this roll of electrical tape. If I push it and there's no friction, what does this thing do? It's going to just slide. If there's no friction, it's just going to slide. If there is friction, it's going to roll, right? It's the friction that actually makes this thing roll. So I need friction to make this thing roll. So if these are rolling, B and C, the object rolls, which means there is friction. As long as we're not pushing at some, I could push here and make it roll. But if this thing is moving, if it's just sliding without friction, it won't roll. If it's sliding with friction, then there is going to be a rolling motion. So there is going to be friction here. So let's look at B then. So B, we roll down the ramp. So rolling down the ramp, I'm going to have G sine theta pulling this down the ramp. Which way is my force of friction going to be? So this rolls down the ramp. The velocity is down the ramp, so the force of friction is going to be up the ramp. Okay, so let's look at C. This rolls up the ramp. So my acceleration is still down the ramp due to gravity, G sine theta. Gravity is always pulling this thing down the ramp, and again, sine slides down the ramp. Now, as this thing rolls up the ramp, which way is my force of friction? So this one, it rolls up the ramp, so the force of friction is also going to be down the ramp. So this one rolls up the ramp, which means the force of friction is down the ramp. So here, friction and gravity work against each other. So am I going to have a big or small acceleration? So these are opposing each other. So friction and weight times sine of the angle are opposing each other. So is that going to make a big or a small force, big or a small net force? Yeah, so this is going to be a small force, so that's going to be a small acceleration. This rolls up the ramp, friction and g sine theta work together. And I shouldn't write g sine theta, mg sine theta. What am I doing? I drew forces, so I should make this mg sine theta and make that a force. So we have force of friction and the weight times sine of the angle work together. And that means we have a larger acceleration. So if we put this all together, we're trying to go from greatest to least. Actually, I'll leave this here for a second. If you're writing, you can even see my little thing at the bottom. So yeah, so as it rolls down the ramp, the weight times sine of the angle is opposed by friction, so we end up with a smaller acceleration. But when it rolls up the ramp, gravity is trying to pull this down the ramp, and friction is opposing this down the ramp, so I have a bigger force down the ramp, I have a bigger acceleration down the ramp, so I have a bigger acceleration opposing the motion. So we're going from greatest to smallest acceleration. 2, 3, 4, 5, 6. To least acceleration. So which one has the greatest acceleration? 16. So I'm going to say E is the greatest. And then the second most is going to be F. .5, and then the next most is going to be 9.8 for A. And then we get to B and C. B and C were between A and D, so then we have to rank these. So C has a bigger acceleration because the forces work together. And then B has a little bit smaller acceleration because the forces oppose. And then D has the lowest acceleration because it's not accelerating at all. And C, I did a little bit of hand waving with C. There's quite a lot that goes into this, proving that the acceleration is not more than acceleration due to gravity. It's actually not as apparent, and it really depends on what the frictional force is equal to, or the coefficient of friction. But assuming the coefficient of friction is less than 1, this should hold true. So if you want some bonus point somewhere, if you want like an extra point or two to try to get your grade to the next grade point level, you can prove that C has an acceleration less than acceleration due to gravity. So if you want some bonus points, prove that C has an acceleration less than the acceleration due to gravity and show math. Right, so far so good. I think that started out relatively easy. Anyone disagree with this, or did anyone get this fully correct? Good. And again, I care way more about your explanation. So put most of your effort into the explanation. You'll write your explanation just like the one before. Go through, leave your original explanation, and then either you'll write next to it you got it fully correct, or if you got anything wrong, you'll go through and write a correction on a separate page. So very similar to how you're doing your AP test review. Mock test correction. Yeah, so I have to wait a really long time because I can't put out late work. If I put out the test key, then other people can turn it in. So I have to come up with a system to make it to where you have to take another mock test, which means I'm not going to put out the key for a while. I'll put out the key before the AP test, so I will probably just leave it as the raw grade in the grade book because it's just a homework grade. And then any additional assignments that don't count towards the grades, because I can only have 2 grades per week, will go to improving your mock test grade. And then when Lambert puts it out and when I've gotten the majority of people to take the mock test, then I'll put out the key and you can actually go through and correct it. So a long way of saying yes, but it will take a while. And then if you're wanting additional points, just go through and do all the assignments. And if by the end, if we have any assignments that are above the 2 assignments per week, I'm going to put those points towards helping your grade. Right? All right, so I like this question here. We have different force versus acceleration graphs. I like this because this isn't a graph that you see all the time. Just kind of a point that we can always, I can give you pretty much any type of graph. The AP test can give you any type of graph. You should be able to interpret any types of graphs. Again, there's a few ways of looking at these graphs. You can either look at the slope, you can look at the area, or look at the actual position where you're at on the graph. So I could do force times area to get the force times acceleration for the area to get something. I could do force divided by acceleration by doing the slope to get a value. Or I could just say at this certain point for this force, I have this acceleration. So 3 different things we can look at on these graphs. We're trying to rank each situation according to mass. So from largest to smallest mass. And then they all have the different scales. So again, care mostly about the explanation. So let's start off with their explanation first. So how do I get my mass from a force versus acceleration graph? Slope or area? This is question mass 24. All right, so slope or area, those are my 2 things. So let's look if I do area. If I do area, that's going to be base times height. So this would be force times acceleration. Or if I do slope, then this is going to be slope is change in y over change in x. So this would be force divided by acceleration, or change in force divided by a change in acceleration. So this is obviously relating to Newton's second law. Net force is equal to total mass times acceleration of the system. Well, I'm trying to get acceleration, so let's divide mass over. So net force divided by mass equals acceleration. So this looks a lot closer to the slope. I want force divided by mass, so not area. And then we should kind of put this into words. So when we say this, I wouldn't want to just write this equation here. We could say something like slope is found by dividing the change in my y value by the change in the x value. So for this graph, slope gives the change in force divided by the change in acceleration. Why did I divide by mass here? Divided by acceleration. Well, I know I divided by mass. It's just because that's why I'm so used to dividing by. But yeah, we're really dividing by acceleration. We know net force equals mass times acceleration, which means that mass is force divided by acceleration. So talk about the graph, talk about taking the slope is force divided by acceleration. From our Newton's second law equation, we see mass is force divided by acceleration. And that means we will rank the slopes of the force versus acceleration graphs to rank the masses. And specifically, we'll see a large slope means a large mass. And we could also just look at the graph itself. If this has a large slope, like let's look at this one right here, or let's look at this one. This is a really big slope. If this has a big slope, it means I have to have a really big force in order to have any change in acceleration. So I need a really big force for a small acceleration. If this has a small slope, I only need a really small force for a big acceleration. So if I need a big force for a small acceleration, I obviously have to have a really big mass because it's hard to accelerate it. If a small force causes a big acceleration, obviously this is a small mass. So we could have even looked at that. You didn't even have to go through slope to describe these. So ranking these from greatest to least, so write up your ranking on the screen. Most to least, give your ranking. No one wants to give their ranking? All right, there we go. So F is the steepest, and then C looks like the second steepest. Now, E is obviously the least steep, and then B is a little bit less steep. I have difficulty seeing the difference between A and D. A looks like it's slightly steeper than D, so I would agree putting A here. But A and D are very close. So A might equal D, but I can't. It's not quite enough to make a distinction. I think A is slightly steeper, but yeah, it's hard to tell. So if you put A equals D, then that's close-ish without sitting there with a ruler and actually going through each one and trying to figure it out. All right, I think this one was probably the easiest one out of these, hopefully. But yeah, again, if you ever come across a graph, first go through and read the axes, and then there's a few ways of analyzing them. You're probably either looking at slope or area, but even if you forget to look at slope or area, you can always just kind of analyze the graph, something like big force gives a small acceleration, small force gives a big acceleration. You can always use that to relate to mass. So you don't even have to go and talk about slopes. You can talk about if I have a big acceleration for a small force, I have a small mass. If I have a big force to achieve a small acceleration, I have to have a big mass, even something like that. All right, so far so good. So going a little bit faster than I allotted time for, but that's good. I was hoping they wouldn't take a lot of time, because I'm not trying to crush you with too much work. All right, now on to everyone's favorite topic, trigonometry. All right, everyone loves trig. So here we have 6 figures below represent treasure chests with 2 forces acting on them. So these are the only 2 forces we have to look at. The lengths of the force vectors represent the magnitude of the force. Well, they also just give us the numbers. Rank the situations from greatest to least with regard to the resulting magnitude of acceleration of the treasure chests. If you believe 2 situations have the same magnitude of acceleration, place their letters in the same rank. All right. So we're trying to rank accelerations. Again, we're going to start with our explanation, and then we'll get to our answer here. The explanation is far more important. So how should we start our acceleration? Because we don't give acceleration vectors. We're giving our force vectors. So what's the first thing we need to write in order to relate acceleration to force? And we are going to have to make an assumption here because they don't explicitly state this, but we are going to have to say that these all have the same mass. Well, they give us forces. They're all the same mass. We're trying to get acceleration. Well, the first thing we should probably start off with is Newton's second law. Net force equals that total mass times acceleration of the system, where acceleration is the net force divided by mass. Well, if they all have the same mass, we're trying to find the acceleration. They all have the same mass. That means bigger force causes a larger acceleration. So in reality, what we really need to rank here is our net forces. And I really should be specific, bigger net force, because now we do have more than one forces, so we are looking at our net forces. So let's just go through these each individually. Let's look at A. How could we solve for the net force on A pretty easily? There's something special about that triangle. It's a right triangle. So we have this 10 newtons, and then we have 6 newtons. These are at a right angle to each other. So that makes things really easy. So my net force is just going to be the vector sum of these, which is going to be just Pythagorean theorem, right? I can move one of these vectors over. It would be like this, like this. So this is 10, this is 6. So if this is a right angle here, if I put my 6 Newton vector here, this will also be a right angle. And so my net force is going to be right here, right angle. I can just use Pythagorean theorem. So my net force is going to be the square root of 10 squared plus 6 squared. It's not going to be a super nice number. $11.7 or 11.66. All right, if you ever see a right triangle, try to take advantage of that, because they're making it easy for you. B is a little bit messier here. We have, let's draw this nice and big. We have a 6 Newton force this way. And then we have a 10 Newton force at 45 degrees. Now, we're going to have to split up this vector, right? So we're going to have to figure out how much of this is going in the x direction, how much is going in the y direction. So I have my angle right here. Well, this is the side touching the angle, so this is my adjacent side. This is the side opposite to the angle. So adjacent is going to be cosine, right? Cosine is adjacent over hypotenuse. Opposite is going to be sine is opposite over hypotenuse. So for adjacent, we're going to use cosine. So we have 10 cosine 45 degrees. For this one, we have 10 sine 45 degrees. And I'm just going to evaluate these numbers. I'm not going to worry about square root of 2 over 2, things like that. So we have 10 sine 45. I am in, come on, calculator. Make sure we're in degree mode. There we go, 7.07. And then we should see this whenever we do cosine, it's going to be the exact same number, right? Sine 45 equals cosine 45. So both of these are 7.07. 7.07. So we have our new triangle here. We go 6 this way, 7.07 this way, 7.07 this way. We can combine these together. So I have 7.07 is opposed by 6, so these are going to subtract from each other. So I end up with a triangle up of 7.07. The left wins out over the right, so then I'm going to have over 1.07. And I'm trying to find my net force this way. And again, Pythagorean theorem, so that net force is going to equal to 1.07 squared plus 7.07 squared. All right, so you get 7.15 newtons. Now, this is obviously a lot more math than you're ever going to see on the AP test, but I could easily see them giving you forces that you have to split up. So it's always good to practice our trig. All right, so let's look at C. C is going to be real easy because the forces are just directly opposing each other. So for C, we have 10 newtons one way, 6 newtons the other way. 10 minus 6 is just 4. So my net force for C is just 4 newtons. Should probably be boxing these all in. This is the net force for A. Net force for B. All right, D is very similar to B, except the forces are switched. Now I have 10 newtons this way, and I only have 6 this way. But let's not go through and redo everything. I have my 45 degrees, my adjacent right here, so this is going to be 6 times cosine 45 degrees for my adjacent. And then my opposite is going to be sine 6 sine 45 degrees. So 6 sine 45 is going to be exactly the same as 6 cosine 45. 4.24 right about. 4.24 newtons. So I have 10 this way, 4.24 up, 4.24 left, (10 minus 4.24) is going to be 5.76. This way, and then we go up 4.24. My net force is going to be the hypotenuse. So net force here is going to be square root of a squared plus b squared, so 4.24 squared plus 5.76 squared. Make sure you stop me and ask questions on this one if the trig is still messing you up. I'm trying not to spend a whole lot of time on this so the videos aren't too long, but if you're not able to follow along or you're unsure why I'm doing something, please ask. So the net force on D, correct? Yeah, net force on D is also going to be 7.15 newtons. Then we have E. E is another easy one because the angle between these is already 45 degrees. So we go over 6, up 10. So my net force right here, just a right triangle. So net force is just going to be the square root 10 squared plus 6 squared, which I don't need to calculate again because we already did that math right here. 10 squared, 6 squared. This is an identical picture to this one, just kind of rotated slightly. So A and E look exactly the same. Net force on E is going to be equal to 11.66 newtons. Then we have F. Let's see, how do we want to approach F? So they give us this. This one looks the worst. We're going to go through and make this one a little bit nicer looking. So 6. So if this angle is 60 degrees, this angle is 60 degrees. What is this angle here? Well, we have 180 degrees to work with. Yeah, so 180 degrees minus 60 degrees minus 60 degrees leaves us with 60 degrees left over. So this angle here is 60 degrees. So I'm going to redraw this to where this, actually I can't draw it straight up. It has to be at 60 degrees. Let's draw this 6 newtons straight over this way. But we're going to draw this 10 this way at 60 degrees. It's a lot nicer to deal with, right? We're going to have to do a little bit less trig here. We are still going to have to split up this 10 at 60 degrees, though. So 10 at 60 degrees. So this is going to be my adjacent side, opposite. Again, opposite is sine is opposite over hypotenuse. Adjacent is cosine is adjacent over hypotenuse. So this side is going to be 10 cosine 60 degrees. This one is going to be 10 sine 60 degrees. And you are allowed a calculator. So if you don't have a calculator with really good trig functions, let me know. We might be able to figure out some sort of online calculator that works best. You should be able to use anything else, or you could use Desmos if you have more than one device. If you just have like the one device, that might be hard unless it's a computer. But it is important that you end up with a calculator. Otherwise, you're gonna have to use the values on the back of your formula chart. 10 sine 60 is going to be the weird looking one, 8.66, but 10 cosine 60 should be real nice easy because cosine 60 is 1/2. So our sine is going to be up 8.66. Our cosine is going to be 5. So let me draw this out. We go up 8.66. And then this side, we have 6 to the right and 5 to the right, so we're going to be 11 to the right. Probably redraw this to where we draw our vectors correct, right? We go tell, so we go from the arrow to the end of the next vector. And then our resultant goes this way, so our net force is here. It really should end right there. All right, so net force for this one is going to be really big comparatively. 11 squared plus 8.66 squared. So square root 11 squared plus 8.66 squared. 13.9998, or right around 14 newtons. Questions on any of these before we go through and rank these? All right. So let's write this on this side so it's a little bit easier to track. Net force on E is 14 newtons. So from the greatest acceleration to the least acceleration, 1, 2, 3, 4, 5, 6. So we're just comparing numbers here. E had the most, 14 is the biggest. 14, and then we had two 11.66 newtons. So that would be A and E are equal. So let's write A equals E. All right, and then going down, we have two 7.15s. B and D are 7.15. All right, B equals D. And then C is the smallest down here at 4 newtons. All right, so that's the real math-intensive way, actually going through and proving everything. Just write up anything there if you don't see what I did or want me to go through one in a little bit more detail. Or stick around after this and ask questions, or come to tutorials tomorrow at 1 to ask questions. We can also go through this a little bit in a more simple way. When we look at this, C is obviously going to be the smallest net force. We have all the same vectors, 10 and 6, 10 and 6, 10 and 6, right? So C is going to be the least net force because our forces act exactly in the opposite directions from each other. So this is obviously going to be the smallest force. We can look for the biggest force. The biggest force is when the forces are closest to working together. Well, they're going to be the closest to working together when the angle between these two is the smallest. So I could have just said, oh, hey, this is the smallest angle between these two. So these are the closest vectors to working together. So this is going to be the biggest force. And then we're going to be ranking them through which ones are the next closest. Well, these two are 90 degrees apart. If these two are 90 degrees apart, then these two are the next closest to working together. So those are going to be the next highest force. Well, these two are 135 degrees apart, 135 degrees apart, 135 degrees apart. So these are really close to working and opposite to each other, but not as bad as C. So we could also have just gone through and looked at angles real fast. So you didn't have to go through all this math, right? That's more like what an AP test question would be like. Well, we're really comparing the angles. So the smaller the angle, the closer these are between these two forces, the closest are to working together. So they're going to be the biggest force. F has the smallest angle between the two vectors, so it has the biggest force. Then we would see A and E have the next smallest angle, 90 degrees, so these have the next biggest force. B and D have the next smallest angle at 135 degrees, so they have the next biggest force. And then C are all the way at 180 degrees. The furthest these can be apart from each other, because if it goes down here, all of a sudden the angle is smaller. So these are opposed, so they have the biggest force. So out of all this math, we didn't have to do any of that, but I like math, and I'm sure you all like math also, right? But yeah, there was a lot easier way of explaining this one. Last minute questions before I end the stream. As always, feel free to stick around to ask more questions. All the same to you. So yeah, if you haven't turned in that mock test, please get that in. The faster you get that in, the faster I can put out a key, and that way you can all look at that and actually see how you did. How did the rankings go? Here, I'll write that again. E is the greatest because they're closest to working together. A and E are the next because they're 90 degrees. B and D, 135 degrees, so further apart. And then C, they're opposing each other, so the least. E is A and F. F is this one. Yeah, that is an F. The grade I get for not knowing the alphabet. F. There we go. Sorry about that. But yeah, get your work in. If you have any more questions, stick around and keep asking those. Bug your friends to get their mock test in and all of that. Otherwise, everyone have a nice day.